Good morning, everyone. So as the chairman says, I'm Yonathan Anahory from the Quantum Imaging Lab at Hebrew University. So let me first thank the organizer and the chairman for inviting me and giving me this opportunity. I'm very, very excited to present you this result today. It's the first published result of my lab, and we're very excited about it. And this sort of artist perspective summarize at least the first part of my talk. So it's edge magnetism, and it's also its effect of the magnetic structure on the vortex dynamics. And this thing here is the technique that we use, which is the SQUID-on-tip, that I will introduce briefly for those of you who don't know. So the scanning squid-on-tip microscopy is a microscopy technique that allows magnetic and thermal imaging at the nanoscales. This is an SEM picture of one of our device, a relatively big one, which an outer diameter of about 160 nanometer. And the way it's built on a quartz pipette, and or a glass pipette, and there are two lead leads here that are superconducting, that are separated here by a non-percolating gap. And the idea is that these two lead leads meet at the end of the pipette where the squid lobe is formed. And that allows us to have a squid that we can bring in very close proximity to the sample. And we can make them relatively smaller, below even 40 nanometers. And the idea is to strap this to a scanning probe microscope and to do magnetic and thermal imaging at a nanoscale. So just quickly, the features, so it has a suitable geometry. Why? Because it has a very small loop, and we can get this loop very close to the sample. As a result, it is extremely sensitive. We're talking about sensitivity to a magnetic moment that is smaller than 1/3 of the spin of an electron. Or if you're talking about thermal sensitivity, which I will not talk in this talk, but the sensitivity is better than 1/1,000,000th of a degree at 4.2 Kelvin. And all this with a high spatial resolution, and we can work to a relatively high field, which is not the case for other scanning squid techniques. So I've been in this business for more than 10 years now as a postdoc and as a PI. And sometimes during the coffee break, people would come to me and say, wow, is it that simple? Like, you make it sound a little trivial. And back then, I would, as a postdoc, I was like, well, nothing is trivial, but, you do what you got to do. And, at some point it works. Little did I know that to create this operation on your own, you need to solve what I call the multi-scale problem, where on one side you have, meters and tons of rock that you need to plan, and the displacement and so on. And on the other hand, you need like a nanogram and a nanometer that you need to plan. And all this at some point, after the planning, manufacturing. This is me. If you were wondering where I was during the couple last year, I was there in the bottom, the lowest part of the lab. And you throw some students in the mix that are naive enough to think it's going to be fun to join this new PI and have a good time, and they're brave enough in a certain sense. And then you get a working microscope. And so the lab is now running for a bit more than 2 years. And we've been exploring several topics, going from superconductivity, magnetism, this is the material I'll be talking about today, but also magnetic vial semi-metal. And we have a new work now that we just submitted on VORTEX diodes in ferromagnetic superconductor infrastructure. I took the liberty to add vortex braiding, which is something that is we're really excited about. So I will add this even though it's not in the abstract. So the material I'll be talking about today, the magnetic material, is a chromium germanium telluride, or CGT. It's what you need to know is that it's essentially semiconducting, so it's not conducting at low temperatures. It has a ferromagnetic transition at about 60 K. So people, looked at these, and it's exfoliable, so people look at these flakes. And one of the ways that you can look at these is by proximatizing with a metal and looking at anomalous Hall effect. And what people have seen, other groups, was that you get a small but finite anomalous Hall effect at zero field. So, and they've also managed to do MFM at the same time. So when the sample is fully magnetized, here you see that almost no features on the image. When at some point you get this step in the anomalous Hall signal, this coincides with the appearance of some domains. And then you lower the field, you reverse the field, these domains seems to evolve, and then you again saturate the magnetization on the other side. And this is also true for the lower branch. But the fact that they see here a finite signal lead them to think, okay, this material retains a finite magnetization at zero field. And we believe that this is not the case for at least most of the sample, but we'll talk about this in a moment. Another experiment, and this is more related to the title of a vortex dynamic, another experiment that you can do is to proximatize this ferromagnet with a superconductor and measure just the longitudinal resistance. And this was done again by another group, and where they found that actually at a constant current, if you look at the magnetoresistance, you have an hysteretic behavior that seems to be somewhere around, some sort of coercive field or so on, and they were not so sure why, how to interpret this data. So this was a good opportunity for us, wherever there is a unsolved transport mystery, maybe a microscopy can help. So the first thing is we did the same heterostructure in our lab, and we managed to get a similar behavior. And but we have the advantage that we can have a look at the same time with our microscope. So what I'm going to show you now is a movie of the magnetic structure evolving. And here you have the transport. So now we're at the zero voltage state. And I'm going to raise the field, and you're going to see what happens. So I'm raising the field here. You see this magnetic structure is evolving. And at some point, it becomes very flat. And this is where the resistance starts to go up. On the way down, the magnetic domain appears and coincides more or less with the zero resistance state. And we interpret this as a vortex physicist as a pinning potential. So if you have a very disordered magnet that has a very non-uniform pinning potential, that it pins vortex very efficiently, whereas if you are fully magnetized, then the pinning potential becomes very flat and flux flow can happen very easily. So this is, so we kind of find an interpretation for this phenomenon, but what we found out is we can maybe use this as a way to probe the magnetic state. So why am I saying this? Is because when I look at one image, so this image was prepared, this image is taking at zero applied field, but it saw -1 Tesla. And this image here saw +1 Tesla, but again, take it at zero field. So which one is magnetized, which one is not? Is there a net magnetization? It's very hard to say from the image. So you need some extra, another probe that is more global to tell you what is the state. And here what I will do is I will again show you the transport data for these two samples going up. So if this sample has more domains pointing up because it was at +1 Tesla, it should magnetize more easily in that direction because there will be more domains pointing in that direction with respect to this one. And we can look at both images and at the transport data. And now I will run the movie again. And as you can see, both in the images and in the transport data, these two things coincide each other, which means essentially that the sample has no memory. It's at zero field. Magnetically, it doesn't know if it was at -1 Tesla or at +1 Tesla before, way above the saturation field in both cases. It starts from zero. It doesn't know. So it's not magnetized. We don't need to go all the way to zero field. So this is when we go to zero field and go up again. We can stop, go down and stop and start to go up here. It's the same thing. Right here is the same thing. And you really need to stop in the middle of this voltage state to go up on the other branch. So basically, as soon as we start seeing those domains, the sample, the magnetic sample forgot where it came from. So I bring you back to the initial data that I've shown, and where I told you these guys measured a finite anomalous Hall. Why is that the case? And you know, we thought about many different interpretations. Maybe it's also the effect of the platinum that hybridizes and stabilizes the magnetization. But maybe there is like a tiny part of the sample that does stay magnetized, and we're missing it, even with this transport measurement and even with our imaging. And after looking for a while, we saw that actually the edges of the sample remain magnetized. So this is at the sample. This is the sample interior. This is the sample substrate. This is the edge after an excursion at +1 Tesla at 0 field. And this is the same area of the sample at -1 Tesla. And you see that the edge stayed magnetized but revert the orientation. So, and we tried this this is at a slightly thicker film, and we also see this effect. So now, why would the edge be magnetized? The truth is, we don't really know, but we have a hint maybe. So we looked also at interior, the behavior of the interior as a function of thickness. So this is for very thick. We said there is no magnetization here. When you increase the field, at some point it magnetizes. And when you, so this, I can draw this with my hand, like just a magnetization that goes up until it saturates. And if I go back to 0, it goes, it stays magnetized, and at some point it demagnetizes and it stays here. So I can just anti-symmetrize this picture. So this, we call this the bow tie magnetization curve. And however, so if we are below a certain thickness, around 10 nanometer or so, the sample stays magnetized at 0 field. It does go through a coercive field, as you would expect from a standard magnet. It does saturate, and if you go back to 0, so it does something like this. It reverses its magnetization, and if you go back to 0, it stays magnetized. So for thin films, it behaves like a hard magnet, and for a thicker film, it behaves like this bow tie. Okay, so this, I complete the picture here. Okay, but what does that have to do with the edge magnetism you're saying? So if you look at one of these edges, if you look at, I take here a cross section, I get this peak, and I look at it in the TEM. Well, in the TEM, you see that the edge of these exfoliated films, they're always sort of in a wedge shape. So they have actually a distribution of thicknesses, and there's always a part of the sample that will be thinner. So we think that, and if we indeed consider this part as being a magnet, and we know how many Bohr magnetons to expect per chromium, we can actually simulate this peak rather well. So you can say, okay, but how do you know that is the distribution of thickness? There's a lot of things that happen at the edge. There is like dangling bonds and the unsatisfied bonds, and that could also be the case. And that's, if you think that, you might be a referee number 2. But, we thought about it for quite a while until we realized that there are other edges. So this is an edge, but there's also step edges between two terraces. And at this step edge, you have the same dangling bonds as in an edge. But if you're above the critical thickness, you should not see anything. And it turns out that we had this data, AFM data of these terraces that happen naturally in these van der Waals materials. And you see these nice steps. And this is the image of that area at 0 field. We see absolutely no edge magnetism in the case of step edges. So it really seems that it needs to be at the edge of the sample to be magnetized. So partial summary, thick films, no magnetism in the interior, only at the edges, and thin films below 10 nanometers or so behaves like a hard ferromagnet, or if you want the artist's impression, to remember it better, take it home. So now let me switch gear to the bonus material. So if I say braiding, most of you have something like this in mind. I see Roland is in the audience. So he showed us some nice way to do it yesterday. And people usually think of wires with piano gates, and then you can tune part of it to be in the trivial state and in the topological state, and you have Majorana at the edges. But there might be another way to do this, and it's with vortices. And this is the avenue that we want to present now. So we call this an on-chip braiding device. So braiding vortices using scanning probes was done before, but the problem with this is that it requires to have the scanning probe. We're trying to do it just on-chip. So the way we do it is that we take 3 superconducting loops, we separate it with an insulator, and we put another superconductor on top. So this brown layer we call the control layer, and the green superconducting layer we call the target layer. And this is how it looks like looking from the top and the SEM. And the idea is that you can put vortices in this layer, and maybe you can manipulate them. So if you and the idea here is that we use our microscopy technique not to move vortices, but only to image, to validate our design. So if you cool down at a certain field, you see here a bunch of vortices, and you see here exclusion zones, okay, where there are no vortices, and that makes sense because there the vortex need to thread through 2 superconductors. But what you see here is that there are 3 vortices at the 3 central point of these loops. And if I cool down with a lower field, I can get just a few vortices. And what I can do is that I can apply a current in one of these loops and kick this vortex out. Now if I reverse the current, I can bring it back again. And I can put it here, and then maybe I can absorb it with the other guy here. And essentially I can sum all these steps and play with these vortices. And that's what I'm going to show you now. So we can actually pull the vortices and exchange them, wind them, and braid them. Of course, here it's a niobium diselenide. The target layer is niobium diselenide. I'm not claiming there's a Majorana here that is being braided. But let's say that would be a step like let's say one element of the toolbox if one would want to do it using vortices. And again, I leave you with a partial summary of the artist impression. So there are 3 loops with this vortex in the middle that you can play around with. And with that, I would like to thank the students and my collaborators. So Avia Noah, which is here, who did the CGT work with the niobium diselenide, and Itai Keren, who did also the work with niobium diselenide on the vortex braiding. And I would like to thank you for your attention.
Thanks for your presentation, and we have time for questions.
Yeah, thank you for the nice talk. Just technical question. How do you control the vertical position of the tip while you're scanning?
You mean the...
To set the constant...
Okay, so we couple it to a tuning fork.
Okay.
So we don't... so the coupling is not ideal, and we only poke. Like, we don't control it in real time. So we don't have a feedback mechanism. We touch, retract to a certain height, and scan.
Okay, yeah, thanks.
So how fast can you scan a square micrometer? Like what is the...
So this image is a 6x6 micron. It took about 2 minutes, but so a square micro... it depends, resolution, signal to noise, and so on. But it's of the order of minutes, I would say.
And for the magnetic material, as far as I understand, you consider the number of layers at the edges, but oddness and evenness of the number of layers may also have an effect. Have you considered that, or
We haven't seen any odd even effect in the interior. It seems that all the thicknesses that we looked at behave the same, but we haven't counted. But you know, unless we always had the even number by magic, then I guess we probe both of them. We haven't seen any effect. It's a ferromagnet, not an anti-ferromagnet. So in that sense.